So what exactly is a wave? A wave is basically a disturbance that can cause matter to oscillate up and down or back and forth, with the result of transporting energy from one place to another. Now, there's two types of waves that you need to be familiar with: transverse waves and longitudinal waves. So what exactly is a transverse wave? A good example of a transverse wave is a wave on a string. Let's say if you apply a force and you create a wave on a string. Notice that the wave is traveling towards the right, that is in the x direction, but the oscillations, the string oscillates up and down in the y direction. So as you can see, the oscillations are perpendicular to the wave motion, and that is a feature of a transverse wave. In a longitudinal wave, the oscillations are in the same direction as the wave motion. A good example of a longitudinal wave is a sound wave. In a sound wave, you have regions of high and low pressure. So let me see how I can draw this. So let's say this shaded region is a region of high pressure. And then this lightly shaded region is a region of low pressure. A sound wave is basically a pressure wave. So the pressure oscillates from high to low. When the pressure is high, the molecules in the air are very close together, so you have a region of high density. So that's a region of compression. Where the pressure is low, the molecules are further apart, and so you have a region of low density, or an expansion, also called a rarefaction. So a sound wave is a good example of a longitudinal wave. So the wave is moving in the x direction, and the oscillations are also in the x direction. As it compresses and expands, it's oscillating in the x direction. So that's an example of a longitudinal wave. Another example of a longitudinal wave is a wave on a spring. If you compress and expand a spring, you can create a longitudinal wave. So as you can see, here we have an area of compression, and here is an area of expansion. So the wave is traveling towards the right, and we have regions of compression and expansion, so the oscillations are in the x direction. So that's another example of a longitudinal wave. Now let's talk about the transverse wave. Which looks like a sine wave. The peak is known as the crest, and the lowest point of the wave is called the trough. The distance between the center and the peak is known as the amplitude. And the distance between successive peaks, let's say from here to here, that is known as the wavelength. That's how long the wave is. This is one cycle from these two positions. So that is one full cycle when the wave goes up, back to the middle, and then down and back to the middle. So that's one full cycle. Now you need to be familiar with the words period and frequency. The period which is represented by capital T, it's the time it takes for the wave to complete one cycle. So you could find it by dividing the total time by the total number of cycles, and you'll get the time per single cycle. The frequency is the reciprocal of the period. The frequency is how many cycles that can occur in 1 second. So it's the number of cycles per unit time. And the frequency is 1 divided by the period. The unit for frequency is hertz, or seconds to the minus 1. The unit for wavelength is typically in meters. The wavelength times the frequency is equal to the speed. Make sure you know this equation. You'll need it whenever you have to solve problems. So let's focus on the units here. So wavelength is in meters. Frequency is s to the minus 1, or 1 over seconds. And v is meters per second. That's the speed. Now there's another equation that you need to know. Let's say if you apply a force on a string, you can produce a wave that will travel along the spring. And there's an equation that will help you to calculate the speed of the wave. And here it is. The wave speed is equal to the square root of the tension force that you apply divided by mu, where mu is the mass per unit length, or also known as the linear density. Mu has the units kilograms per meter. So if you don't want to use the letter U, you can replace it with m over L, which, if you want to rearrange that equation, it's the same as the square root of F times the length of the string, divided by the mass. So here's a question for you. If you increase the tension force, what's going to happen to the wave speed? If the force increases, the velocity will increase. And it makes sense because the force is in the numerator of the equation. Anytime you increase the numerator of a fraction, the value of the entire fraction goes up. Now, if we double the magnitude of the force, how will that affect the wave speed? Will it double, triple, quadruple? All you got to do is plug in 2 into the equation, and everything else that's constant, keep it the same or replace it with 1. So if we replace F with 2, that tells us that the velocity will increase by a factor of the square root of 2. Now what if we increase the force by a factor of 4? What effect will that have on the speed or the velocity of the wave? The square root of 4 is 2. So if you quadruple the force, the wave speed will increase by a factor of 2. Now what about the linear density? If we increase the linear density, what effect will it have on the wave speed? Now because mu is in the bottom of the equation, it's inversely related to the speed. So if you increase the linear density, the speed decreases. And it makes sense. If you have more mass per unit length, there's more inertia. And whenever you have an object with more mass, it's harder to move. Heavy objects tend to move slower, and lighter objects tend to move faster. So if we increase the mass per unit length, we should expect that the wave speed will decrease as long as the tension force remains constant. Now, if we increase the linear density by a factor of 4, what effect will that have on the wave speed? So if we replace mu with 4, we have the square root of 1/4. The square root of 1 is 1, and the square root of 4 is 2. So the speed is going to be 1/2 its original value. So if you increase the tension force by a factor of 4, the speed will double. If you increase the linear density by a factor of 4, the speed will be 1/2 of its value. Likewise, if you increase the tension force by a factor of 9, the speed will increase by the square root of 9, or it's going to triple in value. And if you increase the linear density by a factor of 9, the speed is going to be 1/3 of its original value. Let's work on some problems. A tension of 1500 newtons is applied to a 0.5 kilogram wire that is 10 meters long. And we're given the wavelength as well. What is the speed of the wave? Well, we know that we could find the speed of the wave using this equation. It's the square root of the tension force divided by the linear density. So let's find the linear density first, which is mass divided by the length of the wire. The mass is 0.5 kilograms, and the wire is 10 meters long. So 0.5 divided by 10 is 0.05 kilograms per meter. So that's the linear density. Now we could find the wave speed. The tension force is 1500 divided by 0.05. 1500 divided by 0.05 is 30,000, and the square root of 30,000 is 173.2. So this is the speed of the wave on the string or on the wire. Now that we have the speed of the wave, let's calculate the frequency. So what equation can we use to find the frequency? If you recall, the velocity is equal to the wavelength times the frequency. So the wavelength is the velocity or the speed divided by the frequency. But we have the wavelength, so let's solve for frequency instead. That's what I meant to do. So the frequency is the velocity divided by the wavelength. The velocity is 173.2 meters per second. The wavelength is 0.15 meters. So the unit meters will cancel, giving you the unit 1/second, which is hertz. So it's going to be 173.2 divided by 0.15 meters. So the frequency of this particular wave is 1154.7 hertz. Here's another problem that we could try. The crest of a water wave passes a boat every 2.5 seconds. The wave crests are 10 meters apart. What is the period, frequency, wavelength, and wave speed? So let's draw a picture. So let's draw a water wave. So the distance between wave crests are 10 meters. That is the wavelength. So that's the answer to part C. Now notice that the wave passes the boat every 2.5 seconds. The time it takes for a wave to complete one cycle is the period. So the period is 2.5 seconds. So that's the answer to part A. Now the frequency is 1 divided by the period. So it's 1/2.5, which is about 0.4 hertz. Now, how can we find the wave speed? There's two ways in which you can find the wave speed. So let's make some space. The first technique that you can use is the wave speed is equal to the wavelength times the frequency. So the wavelength is 10, the frequency is 0.4, 10 times 0.4 is 4. So it's 4 meters per second. Another equation that you can use is the wavelength divided by the period. This is 10 divided by 2.5, which will also give you 4 meters per second. So you have two different ways to calculate the wave speed. Go ahead and try this problem. What tension force is required to create a wave that has a wavelength of 15 centimeters and a frequency of 13 hertz, using a string that has a linear density of 0.75 kilograms per meter? So go ahead and take a minute and work on this problem. So the equation that we need to find the tension force is velocity is equal to the square root of the force divided by the linear density. So let's go ahead and solve for F. Let's square both sides of the equation. So V squared is equal to F divided by the linear density. So let's multiply both sides by the linear density, and then we can get the equation for F. So F is the product of the linear density times the square of the speed. Now we don't know what the wave speed is, so we need another equation to find it. The other equation that we can use is this equation. The wave speed is equal to the wavelength times the frequency. The wavelength is 15 centimeters. We can convert that to meters by dividing it by 100. 1 meter is 100 centimeters. So 15 centimeters divided by 100 is 0.15 meters. Let's multiply it by a frequency of 13 hertz. So the wave speed is 0.15 times 13, and it's about 1.95 meters per second. So now we could take this value and plug it into this equation. So it's going to be the linear density, which is 0.75 times the square of the wave speed. 1.95 squared is about 3.8, and if we multiply that by 0.75, you should get an answer of 2.85 hertz. I mean, not hertz, but newtons. So that is the tension force that is required to create a wave with the following characteristics. How long will it take a wave traveling from one end of an 85-meter long wire to the other end if a tension force of 300 newtons is applied to the 5-kilogram wire? So we need to find the time it takes to go from one end of the wire to the other end. So let's say this is the wire, and this is point A and point B. Now the wire is 85 meters long. Once you apply a force, and once the wave is created, the wave will continue to move at constant speed. The equation that relates distance, constant speed, and time is this equation: d is equal to vt. We have the distance that the wave travels from one end to the other end. It's the length of the wire, which is 85 meters. We're looking for the time. So what we're missing is the wave speed. So we can find the wave speed using this equation. But first, let's find the linear density. The linear density is the mass divided by the length. The mass is 5 kilograms, and the wire is 85 meters long. So if we divide those two numbers, you should get 0.05882 kilograms per meter for the linear density. Now let's plug it into this formula. So the speed is going to be the square root of the tension force, which is 300, divided by the linear density. 300 divided by 0.05882, that's 5100. And the square root of that number is 71.4. So V is 71.4 meters per second. So now using the equation d is equal to vt, we can now find the time. So the distance is 85 meters, the speed is 71.4 meters per second, and let's solve for t. We can do that by dividing both sides by 71.4. So 85 divided by 71.4 is equal to 1.19. So it's going to take 1.19 seconds for the wave to travel from one end of the wire to the other end. Now let's talk about wave intensity. The intensity of a wave is defined as the power emitted by the source divided by the surface area of a sphere. You can just put A for area if you want. The surface area of a sphere is 4 pi r squared. So intensity is equal to the power divided by 4 pi r squared. The intensity has the units watts per square meter. The unit of power is the watt, and the unit for area is always square meters. It can be square feet, square yards, but the standard unit is square meters. Power is defined as work divided by time. And keep in mind, work is basically the change in kinetic energy. So you can view power as being energy over time. Work is in the unit joules, and time is measured in seconds. So power is the rate of energy transfer. 1 watt means that 1 joule of energy is being transferred every second. Now, since intensity is power divided by 4 pi r squared, we can say that the intensity is proportional to 1 over r squared, where r is the distance between a point of interest and the source. So let's say if we have a source, we'll call it S. And 1 meter from the source, the intensity is measured to be 900 watts per square meter. What is the intensity at a distance of 2 meters away from the source? According to this expression, the intensity is inversely related to the square of the radius. So as the distance increases, the intensity will decrease. This is known as the inverse square law. So if we double the value of r, if we double the distance, what is the effect on the intensity? Well, if you plug it into the expression, if you replace r for 2, since it doubles, 1 divided by 2 squared is 1/4. So the intensity is going to be 1/4 of its original value. So that is 1/4 of 900, which is basically 225. Now, what is the intensity 3 meters away from the source? What do you think the answer is? So if we triple the distance, what happens to the intensity? 3 squared is 9, so it's going to be 1 over 9 of its original value. 1/9 of 900 is 100. So it decreases by a factor of 9. So if we quadruple the distance, if we increase the distance by a factor of 4, the intensity will decrease by a factor of the square of 4, which is 16. So it's going to be 1 over 16 of its original value. Now there's an equation that can help us to get that answer. But let's talk about how to derive the equation first. So we're going to take the ratio of two intensities, I2 divided by I1. Now the intensity, we know it's the power divided by the surface area. So let's assume that these are the different intensities for the same source. So if we have the source S, and if we wish to calculate the intensity at a larger distance away from the source, we can use this equation. So the source is going to have the same power, represented by P. However, R is going to change. I1 is going to be P divided by 4 pi R1 squared. The only reason why I have a subscript for R is because R will change in this equation. the R value that corresponds to I1 is different than the R value that corresponds to I2. However, I don't have a subscript for P because the power of the source remains the same. So we can cancel P in the equation, and we can cancel 4 pi. So this is equal to 1 over R2 squared divided by 1 over R1 squared. At which point, we can multiply the top and bottom by R1 squared. In this case, these two will cancel. So therefore, we have the equation I2 divided by I1 is equal to R1 squared divided by R2 squared. Now in the last example, we said that the intensity was 900 when the distance was 1 meter away from the source. What is the new intensity if we triple the value, if we triple the distance to 3? Now we know the answer is 100, but let's use the equation to get that answer. So we're looking for I2. I1 is 900. R1 is 1 squared, and R2 is going to be 3. 1 squared is 1, 3 squared is 9, so I2 divided by 900 is 1 divided by 9. So let's cross multiply. 900 times 1 is 900, and that's equal to 9 times I2. So now we need to divide both sides by 9. So I2 is 900 divided by 9, or 100. So you can use that equation to find the new intensity at a different distance if you have another intensity at a certain distance. If you recall from the simple harmonic motion of springs, the elastic potential energy is equal to 1/2 kx squared, where x is the distance or the displacement of the spring being stretched or compressed from its natural length. Now the maximum displacement is known as the amplitude. The mechanical energy, which is the total energy of the system, it's 1/2 k times a squared. So therefore we could say that the total energy of the system is proportional to the square of the amplitude. Now we know that intensity is power divided by area. And power, you can view it as energy divided by time. So notice that E is on top. So we could say that intensity is proportional to energy, which is proportional to the square of the amplitude. So therefore intensity is proportional to the square of the amplitude. So if you increase the amplitude, the intensity will increase. If you double the amplitude, the intensity will increase by a factor of 4, because 2 squared is 4. Now, we know that intensity is inversely related to the square of the radius. And we have the equation I2 divided by I1 is equal to R1 squared divided by R2 squared. Because it's inversely related to it, notice that the subscripts are flipped. They're opposite of each other. But the intensity is directly related to the square of the amplitude. So the subscripts are going to match. Since we have I2 on top, we're going to have A2 on top. So it's going to be the square of A2 divided by the square of A1. So therefore, these two are equal to each other. So if we take the square root of both sides, we're going to get this expression. A2 divided by A1 is equal to R1 divided by R2. So this tells us that the distance is inversely related to the amplitude. So if we increase the distance by a factor of 2, the amplitude will be 1/2 of the original value. The amplitude is inversely related to R, but not to the square of R. It's inversely related to R to the first power. So if we triple the distance, the amplitude will decrease by a factor of 3. If we quadruple the distance, it's going to decrease by a factor of 4. If we cut the distance in half, the amplitude will double. If we reduce it to 1/3 of its original value, the amplitude will triple. So make sure you understand that. So now let's work on some problems. Let's start with this problem. A lamp emits 500 joules of energy every 4 seconds. What is the rate of energy emitted by the lamp? The rate at which energy is transferred is power. And power is basically the energy divided by time. Work is equal to the energy that's transferred. So it could be work over time or energy over time. So it's 500 joules divided by 4 seconds. 500 divided by 4 is 125. So the lamp emits 125 watts of power. So that means in 1 second, it transfers 125 joules every second. So in 4 seconds, it transfers or emits 500 joules of energy. Now what about part B? What is the intensity of the light source 1 meter away from the lamp? So we can use this equation to find that answer. So it's going to be the power, which is 125 watts, divided by 4 pi times 1 squared. So 125 divided by 4 pi is 9.95 watts per square meter. Now what about part C? What is the intensity 2 and 3 meters away from the lamp? So let's draw a picture. So let's say this is the light source. And we know at a distance of 1 meter, the intensity is about 9.95 watts per square meter. So how much is it 2 meters away? And how much is it 3 meters away? As you move away from the light source, the intensity decreases. It's brighter when you're closer to the lamp, but it appears dimmer or less intense when you move away from the lamp. Now, according to the inverse square law, if we double the distance, the intensity is going to be 1/4 of its original value. So we can take 9.95 and just divide it by 4. And so you should get an answer of about 2.49. So that's the new intensity at a distance of 2 meters. Now what about at a distance of 3 meters? So it's going to be 1/3 squared, which is 1/9. So it's going to decrease by a factor of 9. So we need to divide 9.95 by 9. And you should get the answer 1.1 watts per square meter. The intensity of the sun at a certain location on Earth, let's say it's 1200 watts per square meter. How much solar power can be received on a rectangular plot of land that is 30 meters by 40 meters? So let's say if here we have a rectangular plot of land and it's 30 meters by 40 meters. And let's say this is the sun, and it shines its rays across this rectangular plot of land. So how much solar power can be received? So we're looking for the power in watts. How can we find the answer? And we have the intensity. So we know that intensity is power divided by area. In this case, we don't need a surface area of a sphere. What we need is just the area of the region that receives the solar light. In this case, the area of a rectangle. So power is intensity times area. If you multiply both sides by A, you'll get this equation. So what is the area? The area is basically length times width. 40 times 30. 4 times 3 is 12, so 40 times 30 is 1200. You need to add the two zeros, so it's 1200 square meters. The intensity is 1200 watts per square meter, and if we multiply that by 1200 square meters, the unit square meters will cancel, giving us the power in watts. So what is 1200 times 1200? 1200 squared is basically, it's a big number. It's 1,440,000 watts. So that's how much power is being received by this plot of land. So now we can answer the next part. How much energy in joules can be collected in a muff given a power of 1.44 times 10 to the 6 watts? So if you recall, power is energy divided by time. So if we multiply both sides by T, we can see that the energy is power multiplied by time. The power is measured in watts or joules per second. So if we multiply by the unit seconds, we can get the energy in joules. So how many seconds are in a muff? Let's find out. So let's start with one muff, and we know that there's 30 days in a single muff, and in a single day there's 24 hours, and in each hour there's 60 minutes, and in a single minute there's 60 seconds. So the unit months cancel, days cancel, hours will cancel, and minutes will cancel. So it's going to be 30 times 24 times 60 times 60. So there's 200, well, it's actually 2,592,000 seconds in a muff. So now we can calculate the energy collected. So it's going to be 1.44 times 10 to the 6 watts, which is really joules per second, times 2.592 times 10 to the 6 seconds. So as you can see, the unit seconds will cancel, giving us the total energy in joules. So let's multiply these two numbers. So this is equal to 3.73 times 10 to the 12 joules. So that's the total amount of energy that will be collected in a month. By the way, 10 to the 6 represents a million, 10 to the 9 represents a billion, 10 to the 12 represents a trillion. So you could say it's about 3.73 trillion joules will be collected in this plot of land in a single month. The intensity of a light source is 48 watts per square meter at a distance of 30 centimeters from the source. What is the intensity of the source at a distance of 15 centimeters? So let's say S represents the source. At a distance of 30 centimeters, the intensity is 48 watts per square meter. So if we move closer, should the intensity go up or down? So let's say if we're at 15 centimeters. Whenever you move closer to the source, the intensity goes up, so it should be higher than 48. So we know that the intensity is inversely related to the distance squared. So if we plug in 1/2, 1/2 squared is 1/4. 1 divided by 1/4 is 4. So it's going to increase by a factor of 4. 48 times 4 is 192. So this is the answer. But let's use the equation to get the same answer. So it's I2 divided by I1, which is equal to R1 squared divided by R2 squared. So we're looking for the second intensity. The first one is 48. The distance that corresponds to it is 30 centimeters. Now, because we have a ratio, we don't need to convert the centimeters into meters. We can keep it in terms of centimeters because those units will cancel. R2 is 15 centimeters. So how can we solve it? 30 squared is 900. And 15 squared is 225. 900 divided by 225 is 4. So I2 divided by 48 is equal to 4. So if we cross multiply, I2 times 1, which is I2, is equal to 4 times 48, which we know it to be 192. So it's 192 watts per square meter. So what does this number mean? This means that if you have a rectangle, or rather a square, that is 1 meter by 1 meter, it's going to receive 192 joules of energy every second. So this time we're dealing with amplitude and distance. So let's say this is the source, and at a distance of 2 centimeters, let's say this is 2 centimeters, the amplitude is 30. What is the amplitude at a distance of 1 centimeter? 4 centimeters. And 6 centimeters. So if you recall, the amplitude is inversely related to the radius. So if we double the distance, the amplitude is going to be 1/2 of its original value. So at 4 centimeters, it's going to be 15. And if we triple the distance, it's going to be 1/3 of its original value. 1/3 of 30 is 10. And if we cut the distance in half, 1 divided by 1/2 is 4. I mean, not 4, 2. So it's going to be twice as large. So if we move closer to the source, the amplitude is going to double. It's going to be 60. Let's use the equation to find the amplitude when it's 6 meters away from the source relative to this point. So we're going to say A1 is 30, and we're looking for A2. R1, the distance that corresponds to A1, is 2 centimeters. R2 is 6 centimeters. So if we cross multiply, 30 times 2 is 60, and that is equal to 6 times A2. 60 divided by 6 is 10, so we get the same answer. Now we're going to see how intensity is related to amplitude and frequency. Let's go over some equations. Now we know that the period of a spring is 2 pi times the square root of m divided by k. And we also know that the mechanical energy is equal to 1/2 k times the square of the amplitude. So let's solve for k in this equation. Let's do so by squaring both sides of the equation. T squared is equal to 4 pi squared times m divided by k. Now let's multiply both sides by k. So we have the expression kt squared is equal to 4 pi squared times m. And if we divide both sides by t squared, k is 4 pi squared m over t squared. Which I'm going to rewrite it like this. Frequency is 1 over t. So f squared is 1 over t squared. So therefore, we can replace this with f squared. So now we can replace k with 4 pi squared m squared. So E is equal to 1/2 times 4 pi squared times the mass times the square of the frequency and the square of the amplitude. Half of 4 is 2, so the energy is basically 2 pi squared times the mass times f squared times a squared. Now our goal is to get the intensity in terms of the area and the frequency. So let's focus on m, the mass. Mass is density times volume, because density is mass divided by volume. And if we draw, let's say, a rectangle, and let's say this is the cross-sectional area of the rectangle. The volume of this rectangle is the area of the cross-section, let's call it S, times the length of the rectangle. So it's S times L. So right now we have m is equal to P times S times L. Now we know that D is equal to VT. And length and distance, they share the same unit, which is meters. So we could say L is equal to the velocity of the wave multiplied by the time. So m is equal to PS, and we're going to replace L with VT. So we have the equation E is equal to 2 pi squared density times the cross-sectional area times the velocity times the time, f squared times a squared. Now we know that power is energy divided by time. And the energy is 2 pi squared PSV times t times the square of the frequency and the square of the amplitude. So we could cancel the unit t, or the variable t. So now we have the equation of the power of the wave. So now we could find the intensity. Intensity is power divided by area. In this case, the cross-sectional area is represented by the letter S. So it's P divided by S. So that's 2 pi squared P times S V F squared A squared divided by S. So the intensity of a wave is 2 pi squared times the density of the medium that the wave travels through times the velocity of the wave times the square of the frequency and the square of the amplitude. So as we mentioned before, the intensity is proportional to the square of the amplitude. We talked about that earlier. But also you could see that the intensity is proportional to the frequency. So I2 over I1 is equal to A2 divided by A1, but squared. You can also write a relation between intensity and frequency. I2 over I1 is equal to F2 divided by F1, but squared as well. Now the last thing that I'm going to talk about in this video is the principle of superposition. I won't spend too much time talking about it, but all you need to know is that waves are additive. For example, let's say if we have a wave which has an amplitude of 1 and another wave which has an amplitude of 2. And notice that these two waves are in phase with each other. They both have a positive value at the same time. So if these two meet together, they will create a larger wave with an amplitude of 3, which is the sum total of the two individual amplitudes. So this is known as constructive interference. Whenever two waves add, and if they add in such a way to increase their amplitude, you have constructive interference. Likewise, two waves can be out of phase. Let's say if you have wave 1, which has an amplitude of 1, and wave 2, but let's say it's out of phase with wave 1, and let's say its displacement is -2. When these two add, 1 plus -2 is -1. So you're going to get a reduced wave. That's an example of destructive interference. And if the two waves have equal amplitudes but opposite in value, then they will cancel out, producing no wave, or a wave with a net amplitude of 0, which is basically nothing. So that's another example of destructive interference.